Thank you. Appreciate that introduction, and thank you for having me here today. Today, my talk is about why checking your infrastructure as code for misconfigurations is not enough, and what we need to do to really secure cloud-native applications. And I know a lot of the audience may not be as familiar with some of the concepts or technologies that we'll be talking about, so I'll give a quick primer, and then we'll dive into it. So a little bit about myself. I was counting yesterday as I was preparing this slide as to how many years I've been in the industry, and definitely makes me feel old. I've been in information security for 18 years, long enough where, the term cybersecurity makes me cringe. Started off doing security research, focused on critical infrastructure security, then moved on to academia to work on trusted computing and tamper-resistant systems. And then from there, joined the corporate world, worked with a lot of large organizations, especially in the healthcare space, to help them build security architecture practices, to really look at security architecture and how it fits into modern development life cycles. And then today, I am working on my own startup. I'm co-founder and CTO of Oak9, where we're building automation capabilities to secure cloud-native applications. So today's talk is about some of the trends that we're seeing with cloud-native applications and what we as security practitioners, as developers, as DevOps engineers need to do to really address security for cloud-native applications and where we're falling short today. And what I'll do is I'll just start off with a very quick primer on infrastructure as code, just so we're all on the same page. So if I look back to my career, and I just look back 10 years ago as to how software and infrastructure was delivered, there were two different teams that had to work together to deliver that software. You had your software development teams and your infrastructure teams. What has fundamentally changed today is now infrastructure is designed and delivered as code. And more, this infrastructure as code is falling under the umbrella of software development. And we are affording it all of the best practices that we've learned from a software development standpoint. And this is allowing development teams as a whole to accelerate at incredible velocity. So if we look at some of the surveys and results from those surveys, developers are seeing over 100x increase in velocity. Businesses see more agility as well as velocity. And fundamentally, what infrastructure as code allows you to do is it automates and simplifies your infrastructure provisioning. So if you're not familiar with infrastructure as code, it is a declarative way for you to define your infrastructure and the overall architecture that infrastructure represents. And it provides organizations with a lot of benefits. Besides, kind of simplifying and automating your infrastructure provisioning, it's repeatable, scalable, version controlled, modular. There's a lot of benefits in just maintaining complex architectures this way. One of the reasons why most organizations shift to infrastructure as code is because, a lot of companies over the last, 15 years, as they started moving towards the cloud and really shifting their workloads in the cloud. Initially, most organizations go through a lift and shift approach where they're really moving from on-premise data centers and moving VMs into the cloud. And when you take that approach initially, right, you don't necessarily see all the benefits of cloud capabilities because you're not seeing that velocity and agility quite yet. And so what organizations do is they start breaking up their monoliths into microservice-based architectures and really leveraging the native capabilities that the cloud service providers offer. And that's where these organizations really start seeing that those benefits around velocity and agility. But when you move towards these cloud-native architectures, what fundamentally happens is your applications become more complex. They're harder to manage. And from an infrastructure standpoint, right, if you were doing ClickOps to deploy all of these different cloud native capabilities, it becomes unwieldy. You would need an incredibly large infrastructure team to support that. And so this code really helps automate and simplify that provisioning and helps you move faster and deploy infrastructure in a version controlled way. And if we look at what cloud native application architectures look like today, they're incredibly complex. The advantage of using infrastructure as code is it lets you manage that complexity, but at the same time, now you can build even more complex architectures. And this is an example that I pulled from a blog post. This is a architecture of a social media platform. And the details of it are not as relevant as, anyone looking at this particular architecture can see that there's a lot of complexity. There's a lot of different components. They're all interacting with each other. And if you were a security architect assigned to assess this application architecture, it is a daunting task to understand all of the different information flows that are possible here. Threat modeling this application architecture would be quite the endeavor. And that's fundamentally the challenge that security organizations are facing today. And now, this entire cloud native architecture today is actually represented in infrastructure as code. And if I were to just take a rough estimate of what this application architecture would look like based on kind of what I see with my customers today, this would easily be between 10,000 to 50,000 lines of infrastructure as code. And what's missing in this application architecture is a number of different views of this application architecture. So we're missing, configurations around the network. We're missing configurations around identity and access management, user provisioning. And so when it's all put together, this would be an incredibly complex infrastructure as code deployment. And this is fundamentally creating challenges for security teams to really scale to support this trend. How do security teams, get engaged and provide security guidance to that application architecture and impact its security posture? Most of what I see with my customers, and this is prevalent across the industry, is the most predominant approach to allowing security teams to scale today is really misconfiguration checking. So I'll define what I mean by misconfiguration checking. There's a lot of different open source and commercial, tools that help you do this. But essentially what misconfiguration checking does is it queries for specific known configurations of that infrastructure. If it's looking at infrastructure as code, it's doing keyword-based searches to find that configuration and then check to see that it's set to the right value. So as an example, you can search for HTTP protocol in your infrastructure as code and make sure that that key is set to the value HTTPS. And what a lot of these approaches then do is they create hundreds and thousands of these rule sets for each configuration they want to check for each type of cloud resource. And so you have this kind of static database of rule sets that you can then check these application architectures against. And this is an incredibly important endeavor because, as you guys are well aware, we continuously see new cloud breaches, and almost every other day you hear about an S3 bucket that was inadvertently externally exposed. And it's a handful of simple flags that control whether that S3 bucket is internally exposed or externally exposed. And these types of misconfiguration checking approaches can find these really, basic hygiene mistakes that developers often make in a rush to deploy something. And they can catch, a lot of critical issues before they get deployed. And if you're not using TLS for your communication security, and you're allowing HTTP traffic directly, that more likely means that you're not meeting your compliance requirements around the data that's being communicated from one endpoint to another. And so, these approaches then are also really effective in then telling you in the, whenever they identify a issue, that it more than likely creates a challenge in meeting some basic compliance requirements. So I want to talk a little bit about why misconfiguration checking is not enough and why we really need to take a more security engineering approach to the broader problem that we're seeing. And I'll talk about some of the trends in the space. So as we look at modern application architectures today in the cloud, what we are seeing is that the complexity and the size of these application architectures is growing. If you measure this application architecture based on, an entropy measurement, the overall entropy of these cloud architectures are growing. There's more and more connectedness across the different components of these application architectures. And this exacerbates an already existing challenge for security teams. Most security teams that I've worked with, we were constantly firefighting. We were going from one security issue to the next, and you never really had the time to strategically think about the need for security. There are, I think estimates suggest anywhere from like 1.5 to 2 million unfilled jobs in security today. And most organizations are struggling. And as development teams are really shifting towards these cloud native architectures and building more complex architectures, it is really exacerbating that problem for security teams. The other challenge that you see is that the cloud native capabilities are rapidly evolving. So all of the security professionals in the audience today, it's an incredibly hard challenge to then keep up with the different cloud service provider capabilities and how they're evolving, what security capabilities they have, what are the best, design patterns to follow to really approach security for a particular use case in the cloud. And, the other challenge that we're seeing is that more and more development teams are being empowered to take ownership of the entire release management lifecycle, all the way, from design coding to deployment and then the feedback loop back, and as well as observability. And so development teams are really taking ownership of that entire lifecycle. And with that ownership, they're getting the freedom to pick the cloud service providers they want to use, the cloud capabilities they want to use. And so the onus on the security team then is to really become familiar with all of the different technologies that they may be using in their application architectures. And as cloud native capabilities continue to evolve, that's just a continuous learning challenge that all of us face as security architects and security engineers. And I'll give you a data point. Last year in 2021, I believe there were 4 days where AWS didn't make changes to their API, which fundamentally means like their capabilities and their offerings are continuously changing and evolving. And it creates this challenge for security engineers to now stay abreast of all these changes. And finally, I talked about how all of these application architectures are now represented as code. And what that does is it allows development teams to actually deliver infrastructure in an agile way. So from release to release, from sprint to sprint, from deployment to deployment, these developers are now able to deliver infrastructure capabilities iteratively, as customers come to them and say, hey, I have a new requirement and I would like you to perform analytics on this data that you are storing for me in this application. Unlike 10 years ago, where the development teams that I worked with, right, would probably need, a 2-month runway to deliver on a capability like that. Today, experienced development teams can turn around a proof of value within a day. And that type of speed and the rate of change that they're able to make to these application architectures creates an incredible challenge for security teams. And there's a lot of reasons why these application architectures continue to evolve. So one example that I just gave is, business requirements are changing. Another example is where the technology requirements are changing and they want to use new technologies, integrate new technologies into the application architecture, which may fundamentally, impact the security posture of the application. Another example is, security is driving the evolution because security requirements are changing. There may be new compliance and regulatory needs from a security standpoint that this application needs to meet. It may be that, the threat landscape has changed and the types of architectures that security would like to adopt are evolving. And so there's just a whole host of reasons why these applications are evolving, but as they continue to evolve, right, it creates a challenge for under-resourced security teams to keep up and assess the changes that are happening to these application architectures. And one other point before I kind of keep going is that when changes are made to the application architecture, these are foundational changes that if they lead to security issues, there are inherent risks in that application potentially. And not checking for these inherent risks and not addressing these inherent risks before deployment could lead to, severe consequences for your business and for your application. So I want to take a quick detour and talk about complex systems and emergent properties. And we'll talk about ants for a quick second. So, if you were to take an ant and put it on a flat surface, let it walk around, its actions would be erratic, its actions would be random. Eventually, it would tire itself out, and without food, it would likely die. If you took 100 ants, you would probably see a very similar outcome. But now if you had, hundreds of thousands of ants or millions of ants, you would see something different. Together, these ants create a system and they're able to solve incredible challenges. This is an example of ants creating a bridge, but even things like ants moving information, ants figuring out where food is potentially in their environment. They're incredibly intelligent systems that get created, but individually, these ants are not remarkable. It's together and collectively where you see the emergent properties of intelligence that I'm referring to. And, security in a similar way is an emergent property of a complex system. This is from NIST 800-160. It's the System Security Engineering special publication. And they're one of the first kind of industry bodies to really highlight this fact and talk about it. And it's a great read. If you're a security engineer, I highly recommend it. But I'll just read one excerpt from this publication. So security, like safety and other system quality properties, is an emergent property of the system. System security is the application of engineering and management principles, concepts, criteria, and techniques to optimize security within the constraints of operational effectiveness, time, cost, throughout all stages of the system lifecycle. And as we look at the complexity and security being an emergent property, emerging from that complexity, it's really important that we as security engineers, have a grasp of that and we understand kind of how to deal with this as the challenges that we face continue to get more and more complex. And I'll continue on this quick detour and just, talk about different types of emergence and how security kind of falls into that. So, the study of emergence as a topic is something that is still ongoing. This is from some academic research at Indiana University. And I just want to kind of break down how they talk about different types of emergence and where security really falls in this. So if we think about kind of the simplest form of emergence, which is what they call type 1 purposeful interaction, this is really characterized by simple, intentional, designed interactions between components of the system. And most of the security problems that we face today really fall into that type 1 bucket. So, you have two components that are interacting. If you need to think about the potential attacks associated with those components, if you need to think about the defensive measures that you might take, it really falls into that type 1 category. But as you move to, kind of higher levels of emergence, where type 2 really starts talking about, different entities in the system really independently interacting with other entities and receiving feedback and creating more complexity. Now we start seeing more complexity. And as we are moving towards cloud native architectures and we are moving towards, interdependent interactive systems, more and more, right, we are seeing security use cases that fall into that type 2 category. And as an example, like the ants example that I was giving, where ants fall into line, use pheromones to decide how, where to go and how to line up in a formation. That is an example of type 2 emergence. And then finally, type 3 is an example where, you have multiple types of feedback that's happening on different timescales. And when we look at threat modeling and we look at modeling our adversaries and really adding that human element into the overall assessment of security, that's where security challenges start moving towards that type 3 model. Another example that I can give you here is financial markets, where feedback loops, positive feedback loops, create situations where there's a herd mentality and a particular asset class keeps going up in price, but eventually negative feedback loops over timescales, have a higher impact than the positive feedback loops, and the bubble bursts and prices fall. And examples, similar in terms of, security are really, the cat and mouse game that we play between defenders and adversaries is a example of this multi-source feedback, where over timescales things are changing. And the example that I was giving about cloud native architectures and how cloud native architectures are really evolving from release to release, sprint to sprint, and more interactions and connectedness happens within these architectures. We're starting to move towards these type 3 problems, and that's going to create a lot of challenges for us as security engineers. And then finally, type 4, which isn't something that's relevant to today's conversation, but really things like consciousness, right, are categorized under type 4. So with that in mind, let's go back and kind of revisit misconfiguration checking and talk a little bit about why, just doing that, right, is not enough. So the complexity that we're seeing, right, cannot really be addressed through misconfiguration checking. And I want to give some examples, right, of what I was talking about with misconfiguration checking. So let's see if I can. So this is it's an example Terraform module for an AWS application load balancer. And I'll give you some examples of how misconfiguration checking can really help identify some critical issues that might exist in this load balancer. So, you can go into the listener configurations and you can make sure that HTTPS is enabled. You can make sure that this load balancer is only internally accessible versus externally accessible. You can look at the cipher suites that are potentially being used by this load balancer and make sure that it's actually using the latest and greatest cipher suite. So this is not a package of ciphers that you want to use for TLS today. If you're not dealing with legacy operating systems and legacy browsers, there's a much more modern package of forward secure ciphers that AWS supports today. And so all of these things, right, can be identified through misconfiguration checking. Making sure that you're using the right ports if that's something your organization has rules around. Making sure that talking to the target groups, you're actually using HTTPS instead of HTTP, and making sure that logging is enabled. So all of these are just examples of things that we can identify through misconfiguration checking. And as I mentioned earlier, right, the approaches and the tools that kind of perform this analysis, what they're really doing is they're doing keyword searches on this code, finding the right configurations, and then making sure that they're set to a specific static value. And now, if you take this across many, many different types of cloud resources, across different cloud service providers, you can build a database of thousands and thousands of these rules, and then you can start checking for these things, right? So this is an example of a database, and I'm going to, or an S3 bucket, let's take that, right? Where you can decide whether logging and versioning is enabled. You can decide whether what algorithm is being used and whether key management service is being used, or if we're allowing DynamoDB to manage its keys on its own. DynamoDB is a database within AWS, if you're not familiar. And so these are just all examples of kind of individual configurations that we can check for, and we can look at whether or not those configurations are set appropriately. And this is, as I mentioned earlier, right, this is a really valuable thing to identify. It's really important that we identify these types of gaps, but it is not addressing the emergent nature of security, and it is not addressing the complexity of these modern cloud native applications. It is just scratching the surface of what needs to be done from a security engineering standpoint. And what happens with these types of approaches, another downside is really, you create thousands and thousands of these rules, but now you're going to have to create exceptions. So, your particular application use case has a different use case, as a unique use case, and it needs an exception to, 5 of the 1,000 rules that it's being assessed against. And, you'll create these exceptions, and now it becomes, an engineer's full-time job to manage and maintain these exceptions. The other challenge you have is, we talked about how when these types of approaches find true positives, we can almost automatically know that they're not meeting some industry best practice, not meeting some compliance needs. So as an example, if you were dealing with healthcare data and you did not set HTTP protocol to HTTPS, it's pretty obvious that you're going to have some issues with meeting HIPAA regulations, being compliant with high trust. But what these approaches cannot tell you is, what are you doing to actually be compliant? And if we look at the broader needs of compliance, right? So instead of looking at it from the perspective of here are cases where you're failing compliance, what are the cases where actually meeting compliance, and where does the gap exist? That is not something these approaches can do, because fundamentally, right, they look at individual configurations and report on individual configurations. And because of that, right, they have no context of what your application is. If this was your company's cafeteria menu and the daily menu is posted in this application, these approaches assess that menu application in the same way as they would your most business critical application. And so that's kind of another reason, right, why you'll end up having a lot of potential exceptions that you create, and then managing those exceptions. So let's talk about how we need to secure cloud native applications, and how we're going to deal with this complexity that is looming for all of us security engineers. So when we look at the literature and we look at, kind of how the complex systems folks have addressed these problems, we can learn a lot from those approaches. And, there's a lot of organizations, like I talked about, NIST has very correctly identified this. SAPSA many years ago, right, started talking about this. If you're not familiar with SAPSA, they're in security architecture organization that has, methodologies around security architecture. But really, what they've all found, right, is we need to really take approaches that are holistic, as opposed to just looking at individual components of the system. We need to look at the broader system. We need to understand the interactions. we need to look at, and this is what we do when we do threat modeling, right? Is really understanding the system as a whole. What are all of the connections? What are all the data flows? What are all the different components? And how are they interacting? And really taking that holistic systems engineering approach as opposed to looking at individual components and individual misconfigurations. Part of the challenge with the types of complexity that we're seeing in these cloud native applications is, and when we look at security as an emergent property, really the best approach to constrain that is to not let these application architectures get too complex and provide, constrain these application architectures in a meaningful way. And one of the best ways you can do that is as you decompose your application from a top-down perspective, you need to set the right business objectives, the right requirements around security so that you can actually start constraining the security engineering challenge from the very beginning. Reduce the complexity and enhance the simplicity of the design. We don't necessarily, it is not a good thing to have the level of complexity that leads to these emergent properties. And so we want, simpler architecture, simpler designs, very simple design patterns. And then, doing threat modeling to actually holistically look at the system, looking at strategies that assume certain threats and attacks will be successful, and how do we minimize the impact architecturally. So as an example, isolation and segregation is a great approach to look at, separating the impact of one component on the other, so that, if your cafeteria menu is compromised, that compromise should not allow someone to then have a business impact to your business by laterally moving in your environment, right? So how can we build architectures that really limit what the attacker can do if a given application, a given service is compromised? And then as we look at that systems engineering approach, one of the most critical things that you have to do is look at people and process as an integral part of that system, because the human element is really what creates a lot of the complexity in these scenarios, in these systems. And OWASP, has identified this same trend as well. And for the first time in 2021, a new category was added for insecure design. And it focuses on the risks related to design flaws. And the guidance that OWASP has provided is exactly spot on, right? We need to do more threat modeling as security professionals. We need to build security design practices, build our catalog of security design patterns that we want the organizations to follow, define our security design principles, and build reference architectures that developers and our peers can use to build secure systems. And that is really the only approach to addressing this complexity. And so this is an example of the types of guiding principles that we should be establishing as we look at that systems engineering approach to security. Making sure that we are considering security early, that we're building security in, that we're designing security in. Human factored security really considers the end user, it considers the developer. It makes sure that we are actually solving the problems of those end users and not creating barriers for those users and implementers to adopt security. How can we make developers build faster? How can we allow those developers to maintain that freedom in picking the cloud service provider that they want, the cloud capabilities that they want, building the complex architectures that they need to build to solve customer use cases, but doing so in a way that's secure. And things that we as security professionals are quite well familiar with, making sure that there's least privilege, there's separation of privilege. The one big change that happens in cloud native applications is, if you're familiar with least common mechanism, as a way to really minimize shared security controls, the cloud really changes this paradigm. And so The goal here is to really reduce this shared security mechanism so that different applications, different services, are as much as possible, are not sharing those same security mechanisms, are not dependent on those same security mechanisms. Building security that's scalable, thinking about scalability from the very beginning, looking at minimizing the attack surface, defense in depth, and then going back to simplicity, right? Building, as much as possible, building simple security architectures and having an open design so that we're not doing security by obscurity in any of these situations. But even after we do all of this, right, the challenge of the sheer number, the sheer complexity and the entropy that these modern cloud native application architectures have really requires security organizations to embrace automation. And as we modernize our security practices, automation has to be a key pillar of those modern security practices. We need to fit into the development workflows so that we get visibility into every change that happens, but also because, going back to human factored security, we can fit into those development workflows and provide feedback to the developer within their own workflows. We can seamlessly integrate into their day-to-day life cycle so that they are getting security guidance in a timely manner. They're getting security guidance that's actionable, achievable, applicable to what they're doing. But even if we do that, right, we then need to manage for drift. So this application architecture today is no longer static. It is changing constantly. How do we maintain and manage that drift? How do we measure that drift? And so building capabilities to do that and doing so through automation, because there's no way a manual approach will scale to the size and complexity of these application architectures. And that leads me to, one of the core aspects of how security organizations will be able to scale to this problem is using security as code-based approaches. If development teams are leveraging infrastructure as code, security really needs to embrace as a code approaches to build security architectures as code, really thinking about, building dynamic architectures that can seamlessly address the use cases that developers have and help simplify security for developers. So how can security organizations really embrace as a code approaches to build patterns and codify them so that they're not paper documents? We're not delivering Excel spreadsheets and PowerPoint presentations or Word documents. We are looking at using automation to fit into that development workflow, leveraging security as code to assess that application architecture and provide feedback to those developers. And there's a lot of powerful benefits of doing so, right? Those security architectures that you build as code are now version controlled, they're maintainable, they can be modular, they can be flexible, and they can dynamically apply security as this application architecture is changing. So that if the developer starts with the proof of value, and at that point, their business use case isn't dealing with sensitive data, it's not externally exposed, it's an internal proof of value. The security architecture that we apply to that particular application should be different than the one that we apply to the beta version of that same product that evolves and now has more stringent requirements around security. And having that, being able to apply security dynamically is going to be critical to really address the complexity of these architectures. The other big piece of this is visualization. It's really hard to secure what you don't understand. And if you cannot visualize what this application architecture is, what are all the different endpoints that components in this architecture are connected to, what are all the different information flows, you can't possibly, effectively threat model this application to understand where potential issues may lie. And the challenge with visualization in this space is that these application architectures are getting incredibly complex. So, I have customers today that deal with application architectures that have over, 10,000 resources in a given application architecture. And it's all, when you look at application architectures of that size, meaningful visualization is really critical so that you can get the right slice of the information that you're looking for to assess that application architecture. And if we don't solve the visualization problem, we won't be able to really understand what these application architectures are doing and effectively assess them. And finally, one of the most important, probably the most important thing, right? If I can leave you with one thing, is none of this matters, right, if we cannot drive the cultural change that's necessary for security teams to work effectively with the business, with development teams, with ops teams. And there has to be a top-down focus on the people and process associated with how we support cloud-native application architectures. We really need to consider the development teams and the ops teams and the challenges that they have as security professionals, and really have empathy for the types of pressures that they're facing. And similarly, development teams need to have that empathy for the security professionals that are underwater, struggling to, really keep up with challenges across the application portfolio that they may be supporting. And, how do we get to a future where all of these teams can work autonomously, can collaborate effectively, and share responsibility around security, and effectively drive the business to the same goals, so that we can deliver faster, we can deliver more agile applications, and as a businesses can take advantage of new market opportunities, fleeting opportunities that require the organization to quickly react, and how can security be a part of that and really drive that change? So I'll stop with some very simple examples, right, of kind of how this manifests, and where we kind of see these complex relationships, interdependencies, and emergent properties. So let's take, to simplify the example, right? What I'm using kind of a graph visualization here, but let's say you have an application load balancer. If it's a ELB in AWS, then that load balancer, you can configure it to send its logs to object storage. You can configure what logs you want to collect. And then from that object storage bucket, your SIEM solution can pick those logs up. And you might have a serverless architecture that is event-based, where once logs are submitted to object storage, it triggers a serverless function that then notifies the SIEM to go pull those logs. And when you look at, just logging as an example, and, going back to what I was sharing earlier, if I go back to this example, misconfiguration checking will tell me that access logs are enabled. Where's it? Right there, right? So it's telling me that logging is enabled, but that is the extent of what I know based on static misconfiguration checking. Now, if I go back to this particular use case and just that one requirement around logging, and really understanding how we can meet our business objectives around audit and accountability, we need to understand, okay, logging is enabled. Where are logs being sent? What permissions does this load balancer have to talk to that S3 bucket? What is the IAM role within AWS that's been assigned to that load balancer? Is it minimum necessary? Does this object storage bucket, right, is this a shared bucket, or is this purposefully being used for storing logs? Is it limited to this load balancer? And how does this object storage bucket ensure confidentiality and integrity of those logs? Is it configured for versioning? Is it configured for data at rest encryption, if that's a requirement that you have from, say, a compliance framework that's telling you that logs should be encrypted at rest? What else is talking to the storage bucket? What other IAM roles have permissions to this storage bucket? How do logs from this storage bucket end up in the SIEM? What does the architecture look like? If you're using Splunk, for example, right, and you have a solution that's going and picking up these logs or interacting with these logs, How does that interaction work? What are the permissions being set there, and what types of access does that seam have? How is a serverless function defined? And there's a great talk yesterday about serverless security, and are we following all of those best practices for that serverless function? So just to understand whether a single requirement is being met appropriately, there's a lot of nuance in what we need to assess. And if we had to do this at the scale of these complex architectures, right, without automation, this is an incredibly hard problem to solve. I'll give one other example before I pause. Let's say you wanted to have a requirement that all interactions with your databases are inspected for security purposes, and they go through some managed inspection point where you were able to configure rules on what you're checking for. So you can check for things like SQL injection, or you can check for exfiltration of data based on behavioral patterns. And in this use case, right, in a complex cloud native architecture, right, you would need to understand, okay, what are the different microservices or applications that have access to this database? Is there some sort of a gateway here that is actually providing me the capabilities that I need? Do I have an enterprise standard for what types of gateways should be used? What types of capabilities should exist? How are they interacting with the network that these database tables are associated with? How many different database tables do I have? It's easy to spin up new tables in the cloud, and you might have hundreds of these database tables that you need to now protect. And are there other out-of-band channels that essentially bypass that security gateway because they can, there's a security group configured that directly allows access to that VPC. Now, these are pretty standard security engineering and threat modeling scenarios, but what I'd love to point out here is that the complexity of these very simple use cases grows incredibly in these cloud native application architectures because there's just more and more connectedness. And so assessing these types of architectures through a misconfiguration based approach just isn't giving you the complete picture. And if you're an organization that's really looking at, misconfiguration based tooling that's kind of in your pipeline to assess this infrastructure as code, that is important. That has to be a part of the solution, but it cannot be the only solution. If you are not following good security engineering practices, if threat modeling is not part of your workflow, you are missing a big part of the security puzzle, and you are not addressing the complexity, and inevitably you are deploying applications that potentially have inherent risks and are posing inherent risks to your business. So with that, I'll stop, and I'd love to take any questions.